right, welcome everyone to a new seminar on geometry with symmetries. Thank you for coming. And today, my great pleasure to welcome Andreas Kollross from Stuttgart University. And he'll be talking about totally geodesic subspaces in exceptional symmetric spaces. So thanks, Andreas, for joining us.
Okay, yes, thank you for having me in the seminar. So I will speak about totally geodesic subspaces in exceptional symmetric spaces, and this is joint work with Alberto Rodríguez-Vázquez. So let me first start with some kind of introduction. Let's quickly look at the definition. So an isometrically embedded submanifold is called in a Riemannian manifold is called totally geodesic if any geodesic of the submanifold is also a geodesic of the ambient space. And then let's recall some examples. There are elementary examples like the affine subspaces of Rn or great spheres in Sn. Another class of important examples are the so-called flats of Riemannian symmetric spaces. So these are flat and totally geodesic subspaces, which are of importance for the theory of Riemannian symmetric spaces. In particular, the dimension of maximal flats is called the rank of the symmetric space. And also the third example, closed subgroups of Lie groups equipped with the bi-invariant Riemannian metric. So Lie groups with compact Lie groups with bi-invariant Riemannian metrics are examples of Riemannian symmetric spaces. And every closed subgroup is a totally geodesic subspace in this case, which shows that the problem of classifying all these totally geodesic subspaces is maybe not totally trivial, like the first example might suggest. So, and here we are concerned with the classification problem for totally geodesic submanifolds in Riemannian symmetric space. Specifically, we want to restrict our attention to maximal totally geodesic submanifolds, and we only consider exceptional Riemannian symmetric spaces. So that may be a bit strange for many people might think this is strange. So these have not been yet classified for the classical Riemannian spaces, Riemannian symmetric spaces. So you might think this is the wrong order. Usually people study the classical case first, but we study these exceptional spaces. And there are some reasons for that. I will talk about later. Also, it's kind of an interesting subspace. So let me quickly review some earlier classification results of other people on totally geodesic subspaces in symmetric spaces. So the first to mention is, of course, a paper by Wolf in 1963. He classified the totally geodesic subspaces in spaces of rank 1, so in spheres and projective spaces and hyperbolic spaces. And then there's a series of papers by Leung about reflective subspaces. So they are special totally geodesic subspaces, and they are given by the connected components of fixed point sets of an involutive isometry. So if you have some group of isometries acting on a Riemannian manifolds, the fixed point set or its connected components will be totally geodesic. And here we have involutive isometries, so isometries of order 2. And so he studied those and classified those reflective submanifolds. In 1980, Onischik defined the index of symmetric spaces. So this is the minimal codimension of a totally geodesic subspace. So he classified the spaces of index 1 and index 2. So those spaces of index 1 are those which have totally geodesic hypersurfaces. So it's well known that this is only the case if the space, these can only exist if the space has constant curvature. So only for spheres and real hyperbolic space and Euclidean space, there exist totally geodesic hypersurfaces. And Onischik classified those spaces of index 2. Then there's a paper of Ikawa and Tasaki where they classified subspaces of maximal rank in compact Lie groups, and we will later in this talk we will see we will recover some of these results also. Then Chen and Nagano in two papers, 1977 and 1978, they set out to classify totally geodesic subspaces first in the complex quadrics, so in spaces of rank 2, and they have given a classification. But later, when Sebastian Klein in his thesis looked at these totally geodesic subspaces, it actually turned out they had overlooked two examples. So so Sebastian Klein was able to finish the classification of totally geodesic subspaces in spaces of rank 2, from 2005 to 2010. Then Jürgen Berndt and Carlos Olmos in several papers, they classified maximal non-semisimple subspaces. So these turn out they are subspaces which have a one-dimensional flat factor, and doing this, they also could prove what is called the index conjecture. So the index conjecture is what is here written in parentheses. So in an irreducible symmetric space of non-compact type, which is not this particular space. So this space is actually an exception among the exceptional spaces. So you have to exclude these spaces. But for all the other irreducible spaces of non-compact type, so there is always a reflective submanifold whose codimension equals the index, which is just a complicated way of saying there's always a reflective totally geodesic submanifold of maximal dimension, or the other way around rather. So the totally geodesic submanifold of maximal dimension, among them is always one which is reflective. So this is called the index conjecture, and I will come back to this later because we prove something similar. So wait, I have now a small problem.
So maybe you can try sharing screen again. I don't know.
I'm kind of locked in full screen mode and cannot. Oh, come on. Maybe stopping the screen sharing is maybe the thing to. Yeah, that's good. Okay, then let me try again. Okay. Sorry for that. I'm sharing the screen again. Okay, now I go in full screen. Okay, so on this slide, so here's our results. So we have a classification up to isometry, not up to congruence, of maximal totally geodesic submanifolds in those symmetric, irreducible, exceptional symmetric spaces. So, and here is the list. So this is not, so in this theorem, there's a kind of a list, but this is not the result. This is just a list of the spaces where we classified those subspaces. And so the actual result, I will show it, but it's on the last 8 slides of this talk. So there are more than many more than 100 totally geodesic submanifolds that we find here with our approach. And of course, if it is only necessary to state the result for the non-compact case, because the compact case follows by a duality. And we also have this second theorem, which is kind of similar to this proof of the index, of this index conjecture. So we also make this observation about totally geodesic submanifolds whose codimension equals the index. So this means it is a totally geodesic submanifold of maximal dimension. And we make this observation that the so-called Dynkin index of this I haven't yet defined. I will define it later. The Dynkin index of the semisimple part of the isometry algebra of this totally geodesic subspace sigma equals, well, 1, 1, 1. So this Dynkin index will be a tuple of natural numbers. I will define it later. And also observe that this theorem is not only proved for exceptional spaces, we prove it for all irreducible spaces. Okay, so let me, yeah.
So Andreas, may I ask you a question before you continue? So this list, I mean, I haven't studied my real semisimple algebras lately. So is this a complete list of exceptional symmetric spaces?
Yes, yes. These are the exceptional symmetric spaces of non-compact type, irreducible of non-compact type. And that among these, I will talk about this also later. There are again two subtypes. So these are the spaces of rank. Sorry, these are the spaces of type 3. Now
yeah, of course, the complex
and these are the spaces of type 4.
And yes, right. Yes, of course.
So okay.
Okay, thanks.
Can I go on? Okay. So here are some basic notations and some basic notions on totally geodesic subspaces. So always here we will consider a Riemannian symmetric space given as G mod K, where G is the connected component of the isometry group and K is the isotropic group of some point O. And then there's this geodesic symmetry, and we can define an involutive automorphism of G by conjugation with this geodesic symmetry. So this is the sigma, and then we take, as usual in this theory, we take the differential at the identity element. This is called theta, and it's an automorphism of the Lie algebra of G. And as usual, we have the plus and minus 1 eigenspaces and call them K and P, Gothic K and Gothic P. And then we have this decomposition, and this is called the Cartan decomposition of G with respect to theta if we have this condition, if this modified killing form, so B stands for the killing form here. So this minus bx theta y is positive definite. And then in this case, this theta is called a Cartan involution. So one should, yeah, some people always call this decomposition a Cartan decomposition, but we need to stick to this original definition. We only call it a Cartan decomposition if we have this positive definiteness. So in particular, for in our notion here, for symmetric spaces of compact type, the Cartan decomposition is always trivial. So it's always just the K and no P part. So this is kind of, well, somewhat important to keep this in mind, because otherwise some of the statements I will give later won't be true. Okay, and all Cartan involutions are conjugate by inner automorphisms of G. And also, as usual, we can identify the tangent space at this reference point O with this P part of the decomposition. And then, so that it's standard knowledge that the totally geodesic submanifolds are given exactly as exponential images of so-called Lie triple systems in this P. Okay, so linear subspaces L and P, such that this nested Lie bracket LL, and then again you bracket with L again is in L. So this is the condition. So naively you might think that, as always in this theory, you reduce geometric questions to some algebraic question in Lie algebras. So, and then you might think it's the way to go is to attack this question. But I don't know. So I don't know all the literature. I don't know. Maybe this has been done. But my impression is this is kind of too hard to study Lie triple system. So there's no good theory. There's no normal form or something. So and this is also not what we do. So this is kind of, yeah, it's kind of too hard these triple systems to study these triple systems. So instead, what we will do is we study some simpler object. We will study submanifolds, subalgebras of the isometry group. So that's kind of a simpler object. And also these subalgebras are given in tables and they are classified themselves. So, and the reason why we can do is, instead of studying Lie triple systems, just study subalgebras. And yeah, also the reason why we are looking at the non-compact type is this theorem of Karpelewicz-Mostow. So I have two versions here. So the first one is kind of the geometric version. We have a symmetric space of non-compact type. Then any connected and semisimple subgroup H of G has a totally geodesic orbit at some point. So, and you can also state it as in this algebraic version. Here is kind of very general. You have a homomorphism of real semisimple Lie algebras. I mean, you might think F is just the inclusion map of a subalgebra. Maybe it's better to think about it this. And then if you have a Cartan decomposition of this subalgebra, then there exists kind of compatible Cartan decomposition such that the K prime, the image of the K prime is in K, and the image of P prime is in P. So these two versions are actually equivalent, and they are only, so this is only valid for non-compact type, because there are examples of in the compact case, there are examples of subgroups which act without any totally geodesic orbit. So this is also the reason, the main reason why we stick here to the non-compact case. Okay, so we will use this a lot. This is kind of our main tool. And so here I want to recall the 4 types of irreducible symmetric space. But first, let me recall this definition. So if we have a simple real Lie algebra G, then it is called absolutely simple if the complexification, so if I complexify this Lie algebra by taking the tensor product with C, is still a simple complex Lie algebra. So there are two possibilities. Either I complexify and get a simple complex Lie algebra, then I call it absolutely simple, or I get 2 copies of the same, so of the 2 copies of the same complex Lie algebra. This mainly happens, not mainly, but only happens if this G that we started with was already given as the realification of a complex Lie algebra. So if we start with a complex Lie algebra, forget about the complex structure, only admit real scalar multiplication, then we have the realification of a complex Lie algebra. And then if we complexify again, the result will be 2 isomorphic copies of the original Lie algebra. So we have this dichotomy. We always have absolutely simple or non-absolutely simple. And the classification of irreducible symmetric spaces into these 4 types is according to this dichotomy, and also to the compact and non-compact case. So I have given here examples in blue for all those 3 types. So the compact type, the type 1, is where we have a absolute, so a simple compact Lie group G mod K, like this, and so the corresponding type in the duality is this G mod K, where G is non-compact but absolutely simple. So these, as I have written down here, these types 1 and 3 correspond by the duality, and type 2 and type 4 also correspond. So in this other case, we have not absolutely simple isometry algebra. Here in type 2, actually, so here we have compact Lie groups with bi-invariant Riemannian metric. So, and then you can multiply from the left and from the right, and this isometry group reflects this. So it's kind of covered by G times G. So we actually have, as a not even simple Lie algebra, we have 2 copies actually here. So that it's not simple also. So then also not absolutely simple. And here the type 4 is these simple complex Lie groups, and the K is a compact real form. So, but we will restrict ourselves now in the following only to type 3 and type 4 because of this duality. Okay. And now I would like to explain to you what we call the Dynkin index. Well, first of real first of subalgebras, of real Lie algebras, and then also the Dynkin index of certain totally geodesic subspaces. So what is the Dynkin index? So the idea is quite simple to explain. Assume for the moment this Q would be the killing form of, so we have a let's say we have a subalgebra, so a Lie algebra homomorphism from H to G, like here, and then just assume this Q is the killing form, so we can pull, so we have two bilinear forms on H. So we can pull back the killing form from G, and we could also use the original killing form of H. And these do not agree necessarily. So in most cases they don't. And so we get a certain number, this scaling factor. So by Schur's lemma, these two bilinear forms, they agree up to a multiplicative factor. So that's the basic idea to distinguish between isomorphic types of subalgebras by this Dynkin index. But Duncan refined this idea. So here he says we say Q is the multiple of the killing form normalized by the condition that the square of the length of the longest root equals 2. So this is quite a sensible. Otherwise, the numbers get too big, and this is actually a quite clever way of normalizing it. And Duncan also proved that with this definition, this index that you get, so this factor which distinguishes these two bilinear forms, this Dynkin index is always a natural number. And we would now like to extend this to semi-simple subalgebras of simple real Lie algebras. So this definition I just gave is for complex Lie algebras. And so if you look into those lists of Dynkin where those subalgebras are classified, it's quite natural to distinguish them by the Dynkin index. So we would like to extend this. So down here on the slide, we do the first obvious step. So if the subalgebra that we are looking at, this H is not simple, but semi-simple, so is a direct sum of a number of ideals, then we just define the Dynkin index as this tuple of Dynkin indices. So in our definition, it's not necessarily a number, but a tuple of numbers. And then the natural thing that you want to do here is, of course, this Dynkin index. So this Schur lemma holds for complex Lie algebras, but for real subalgebras, we don't know if it's really a factor. We cannot define it analogously. So we kind of have to use the complexification. So the natural number is, of course, the natural idea is that you take this subalgebra H and a Lie algebra G and then complexify both of them. That's the natural idea. But there's of course this difficulty. Sometimes when you complexify, you don't get a simple algebra back, because if the Lie algebra you start with is not absolutely simple, you get two copies. So this is the reason why we have to make this distinction. So here, the first part, we say if G is absolutely simple, then we do this kind of natural thing. So what I show here, this formula, we take the complexification of G, because for our definition to work, we need that the big Lie algebra still needs to be simple. And then we complexify the H and we define the Dynkin index as this. So, but keep in mind, this HC, depending on if H was, okay, here H is not necessarily simple, but even if H is simple, you could get a semi-simple complex Lie algebra here for HC. In this case, you would get a pair of equal natural numbers. So our Dynkin index is a tuple of numbers, and even for simple subalgebras, simple real subalgebras, it might not be one number but two. Okay, and then so the other case, if this G is not absolutely simple, so this happens exactly if it is itself the realification of a simple complex Lie algebra, which I have denoted by L here. So G is LR. And then in this case, of course, it's natural, since we already have a complex structure on this Lie algebra that I now call L here instead of G, of course, I don't need to complexify this, because otherwise I would get 2 copies and Dynkin index again is not defined. So in the natural thing is, because we already have a complex structure, I don't use this HC, but I already have the multiplication with I is already defined in this Lie algebra. So I take H plus IH. And then also, so this H, if this H coincides with a subalgebra of this complex Lie algebra, then this IH doesn't do anything, and we have still the old subalgebra H, and the Dynkin index was defined as before. But if this H is not, if this H is not a complex subalgebra, then this will be some other subalgebra, and then this takes an effect. So maybe you're thinking now, while I'm explaining this, why is he talking so long about such a kind of a simple technicality? But we actually had to think for a long while how we really define this Dynkin index so that it's practical. And we have decided what we have come up with is this definition in the end. Okay, and now we define some new notion, some semi-simple subalgebra of a simple real Lie algebra. They are called isometric if they are isomorphic, and also if they have the same Dynkin index. Okay, and the reason why we want to do this, because we want to somehow, in the end, we want to characterize isometry classes of totally geodesic submanifolds by this Dynkin index. So here we have this theorem which somehow says that we not completely generally, but in many important cases we can do this. So we have an irreducible symmetric space of non-compact type. We have 2 semi-simple totally geodesic submanifolds through the point O. We look at their Lie triple systems and then define this G sigma J of both of these by what it generates in the Lie algebra. And then so in the case where G is absolutely simple, this holds in general, then sigma 1 and sigma 2 are isometric if and only if these subalgebras are isometric subalgebras of G, so are isomorphic and have the same Dynkin index. And in the other case, if G is complex and this J sigma is either a complex subalgebra or real form, then this also holds. So this is enough for this paper. We did not want them to say something more general here, because there are actually some small difficulties here. So now that we have defined it, we define the Dynkin index of a totally geodesic submanifold. So this is actually the index D of sigma, what is written here. So this is this Dynkin index of this subalgebra. This is a numerical invariant which characterizes the isometry classes of semi-simple, well, only maximal totally geodesic subspaces. Otherwise, we don't want to say, we don't know. Okay. And now,
so Andreas,
yes,
if I understand you correctly, so the goal is to understand which symmetric spaces arise as totally geodesic submanifolds of these exceptional symmetric spaces, but not like the multiplicity, or in how many non-equivalent ways they arise, right? Just whether it arises or not.
We actually classify up to isometry. So we give a list of spaces.
But there's 2 notions of isometry here. So you could ask whether they are isometric intrinsically or via,
that's a notion we are using. They are isometric intrinsically with the induced metric. So that's what so we will classify those isometry classes. We do not classify up to congruence. So that would be more, but this is because we distinguish those subalgebras by these isometry classes. So but in most cases, we will see the list. In most cases, these will agree. But okay. Okay, so
excellent.
here, okay. Another thing that we need to do this is, so this is a result of Antonio Di Scala that we have refined here in this paper. We have this situation of the Karpelewicz-Mostow theorem. So we have a symmetric space of non-compact type and some connected Lie subgroup, and then the Karpelewicz-Mostow theorem there says there's always at least one orbit which is totally geodesic. But let's assume we have two of them, which are totally geodesic orbits, then they are congruent in M. So this gives somehow, this is somehow how you say, the uniqueness part of Karpelewicz-Mostow. And it's, of course, important to keep in mind, this only works for non-compact type because the statement is blatantly false in the compact case. So for the simplest of examples, let's take the rotation actions, or the action of SO2 on the two-sphere. Yeah, rotating the two-sphere, we get different isometry class of totally geodesic orbits where we have the equator and the north and the south pole, and they're not isometric. They even have different dimension. So this is wrong. But in the non-compact world, so to speak, we can have this uniqueness. Another reason why it is natural to look at this Duncan index and isometry classes of subalgebras. Okay, and then also some definition that we will need in the following, some notion that we are using here. So if we have a semi-simple Lie algebra in this non-compact isometry algebra, it could also have compact ideals. But these compact ideals, they do not contribute anything to the totally geodesic orbit, because so in this Cartan decomposition, the k parts of these, so these compact ideals will always be in the k part of the Cartan decomposition. So what we really have to look, so somehow we can discard those compact ideals. What we really have to look at is Lie algebras where each simple ideal is non-compact. So this is not the same thing as saying a non-compact subalgebra, which only means there is at least one ideal that is non-compact. But here what we want to say is all of the ideals are non-compact, and so that's why we introduce this notion. A semi-simple Lie algebra is of non-compact type if each simple ideal is non-compact. So that's what we are looking at from now on. And then we have this correspondence theorem, which kind of explains our method. So this is kind of central for our method. We have an irreducible symmetric space of non-compact type. H and G is a subalgebra. And then sub is a subalgebra which is maximal among those subalgebras of non-compact type. Then there is some totally geodesic orbit which is maximal, which is a maximal semi-simple totally geodesic submanifold. So all these subalgebras of non-compact type give us semi-simple totally geodesic submanifolds, but we are only interested here in the maximal ones. So we have to use, and here we are looking at those which are maximal among the semi-simple ones. So we have to look at those subalgebras which are maximal among those subalgebras of non-compact type. So this is kind of, there are some fine points. So this is not the same thing as subalgebras of non-compact type, which are maximal among. So we will call them maximal subalgebras of non-compact type here. And also the converse is true. If we have a maximal semi-simple totally geodesic submanifold, then there is a subalgebra which is maximal among those subalgebras of non-compact type. So taking everything together, this says what we, to classify those maximal semi-simple totally geodesic submanifolds, and recall the non-semi-simple ones have already been classified by Berndt and Olmos. So we classify all of the maximal totally geodesic subspaces. We can focus on those which are semi-simple. So this will be our method. In this theorem, we will classify the maximal subalgebras of non-compact type, well, only in the exceptional non-compact simple real algebras. Okay, so okay, and then we can state this a bit more in detail, a bit more technically in this definition. We here, so G is this Lie algebra of the isometry group of a non-compact irreducible symmetric space. We define this curly L of G as the set of isometry classes. So we only need to distinguish them up to isometry because we have this theorem: if they are isometric, then also the totally geodesic subspaces which correspond to them will be isometric. So if you want to classify up to isometry, we have to look at these isometry classes, and we denote them like this as a pair where H is the isomorphy type of the subalgebra, and the second entry is the Duncan index. So this is the way to denote these isometry classes. Okay, and then corollary now this is kind of obvious now, this set L of G of isometry classes is in one-to-one correspondence with the set of isometry classes of maximal, semisimple, totally geodesic submanifolds. So this is now what we have to classify. This is what we have to find, this L of G, this set. So how do we do this? How do we classify those subalgebras? Actually, okay, let's start with the simpler of the two cases. The simpler case is the case where the G is not absolutely simple. And this was also already done by Ikawa and Tasaki. So I will do this first. So here G is a complex simple Lie algebra. And then and of course, we look at the realification actually, and H is a maximal subalgebra of non-compact type in this realification. Then we have that H coincides with one of the following in this list. So, well, there's this in Duncan's work, there's this dichotomy of R subalgebras and S subalgebras. So what is this? So an R subalgebra is one which is contained in a regular subalgebra. So a regular subalgebra is one which is given by a subset of the roots, I say simply. So, but if we have a maximal and R subalgebra, if it's contained in a regular subalgebra, then of course it's also maximal, then it's regular itself, of course. Or otherwise it's a maximal S subalgebra, which is not contained in a regular subalgebra. So we have these two. So these two are the case if the subalgebra itself is it coincides with a subalgebra of the complex Lie algebra, but it can, since we are looking only at the realification, it can also be a non-compact real form. So this is the set L of G. So in this case, it's kind of easy, also was known, and yeah, also the converse is true. So this is actually then, in this case, the classification that we want to do. I will show you this set L of G on this slide. So there are 5 cases. So here we are only looking at the spaces of type 4, right? So we only look at complex Lie algebras. So let me, I don't know, maybe it's not really necessary to look at all of these cases, of course. So let me just explain them. Let's start with the first row here. So what does this mean? So in G2C, so they are the complex, so not of this complex Lie algebra, but of its realification, there are the following maximal subgroups. So there's one which is SL2C plus, so 2 copies of SL2C, and the Duncan index is 3, 1. So this is a pair of numbers because this Lie algebra is not simple. So we get 2 numbers. There's also an SL2C with Duncan index 28 and an SL3C with Duncan index 1. And then this last one is of a different type. This is a non-compact real form of G2. And these other entries in the tables are similar. Let me just say quickly this, in case someone is looking at this and wondering why do I have 3 numbers, but not, this is just a short notation for, there are 3 of these subalgebras, and there's one with Duncan index 520, one with Duncan index 760, and one with Duncan index 1240. So these are known and can be taken from those tables of Dynkin, where he classifies semisimple subalgebras of semisimple complex Lie algebras. So this is kind of the let's say easier part. Also was already known, but now let's go to the part which was not known. How do we classify those Lie algebras in curly LG, those maximal subalgebras of non-compact types? Well, actually, we don't do it ourselves. So thankfully, there are two classifications already that we can use. So this is, the first one is in the paper of the Graaf-Marrani from 2020. So they classify for all absolutely simple real Lie algebras of rank less or equal than 8, all the maximal reductive subalgebras H, whose complexification is a maximal reductive subalgebra of this GC then. So this GC is then simple because G was absolutely simple. So this is the case we are looking at, is absolutely simple G, but, and well, also reductive is not actually what we want, but it gives us, so all the Lie algebras we are looking at are at least will be contained in this set if the complexification is maximal. So, but it can actually happen that the complexification of the subalgebra is not a maximal reductive subalgebra of the complexification. This can also happen, but there's also another paper of Komrakov, 1990, where he exactly studies this case. So also the same thing. So the maximal subalgebras are given for the case when the complexification is not a maximal subalgebra. So now we are kind of, well, not really done here. We call the result of joining these two lists L tilde. But one has to keep in mind that this is not, these are maximal subalgebras, and we take the reductive, we can restrict our attention to the semi-simple ones, but it's actually not exactly what we wanted to classify, because remember, we wanted to classify those which are of non-compact type, so where all of the ideals are non-compact. But in these lists, there are also some subalgebras which sometimes have a compact ideal. And so they are not maximal of non-compact type, they are non-compact, but not, they are maximal, they are non-compact, they are not of non-compact type. They may have a compact ideal. Okay, maybe first idea is of course then say, okay, so what, let's just delete this compact ideal. But then if you do this, it's not clear anymore if the resulting Lie algebra is maximal of non-compact type. It could be, could be not. We have to find a criterion to decide this, but we have done this, so I can show you, well, at least this list L tilde here. So there's, let me go quickly back, forth and back. So for all those types of not absolutely simple G, so these are also all these forms, so it doesn't fit on one slide. Let me just look at the first row. So there are these subalgebras similar as before. And it sometimes happens like here, where the cursor is, there is a compact ideal. So this SO2, we have deleted it, but we have decided to keep it in the list, so to make it easier for people who want to compare, to check our lists against the list of the Graaf-Marrani and the lists of Komrakov. So we have decided it makes it easier to keep them in, but just to strike them out, so you can see. So actually, what is here is without these simple ideals. So this is this LG. Maybe I don't comment so much. It's similar than the other list. It makes no sense of going through all this. So these, you see, we get quite a lot of examples, actually surprisingly many examples in the end. But then if you have these compact ideals, like here, this SU3, of course, also R for us is a compact ideal, because compact Lie algebra means it's the Lie algebra of a compact Lie group. So this would be an SO2 two-factor. Maybe it is. We don't really know, but we have to decide which of them we still have to keep. So if we have these compact ideals, we need a method, or we could do this ad hoc in any case to decide if the resulting Lie algebra is still maximal of non-compact type, or if we have to discard it. So, and then after having done several of these cases, so to speak, by hand, we came up with a general method. So to decide this. So here's the situation. Let me explain. We have a reductive subalgebra. Well, algebraic reductivism doesn't make such a big difference. A reductive subalgebra, which is a direct sum of these ideals K0 and G1. So the K0 is a compact Lie algebra. And we also assume that it's already compatibly embedded with respect to the Cartan decomposition of G. So which can always be done according to Kapelewicz-Mostow. So then the following holds. So we have this H intersected P is a Lie triple system, and we have a totally geodesic orbit of this action here. So we need to decide if this is maximal or not. But we have also this this thing here in number 2. K0 acts almost effectively on the normal space, but it acts trivially on this L, because these are different ideals of they commute. So it acts trivially on this orbit. So the situation is kind of we have an orbit, but we have to decide if it's maximal. How could we disprove that it's not a maximal totally geodesic submanifold? Well, we have to show there is someone in between. We have to show there is a totally geodesic submanifold which contains all of this orbit and which is bigger, but which is not the whole space. So what we have this K0 action, it acts trivially on the orbit. That's good, because then we want to produce this totally geodesic submanifold as a fixed point set. So this orbit given by the exponential image of L will be contained in the fixed point set. And then this is a bit complicated to read here. Maybe you should not really look this up. How says if we find some vectors in the normal space, so some of them are left fixed. So this vector V is left fixed by this, and actually we don't have to take K0, but it's enough if there exists a subgroup Q. One of them is left fixed, this V, and one of them is not left fixed. So we find a fixed point set which is kind of in between the whole space and this totally geodesic orbit. So it differs from this totally geodesic orbit because it is bigger. We have some vectors in the normal space which are still left fixed, but not all of them in the normal space are left fixed. So this guarantees then we have really something in between, so a proper totally geodesic submanifold which contains this, which properly contains this orbit. So then we can use this, and then this in blue is a technical condition. You can think further, when is this automatically fulfilled? So this is kind of convenient just to rule out those let me quickly go back, those subalgebras where there's a compact ideal that is striked out here in this list. So we can do this. So this is the last step. So then we get those maximal subalgebras of non-compact type, and now we get the lists. And now I will. So at the end of this talk, I will show you the lists of those subalgebras. As I said, it takes 8 slides to show all of them. Is more than 100. So of course, it's no. Let me show you the first one. So I used colors to set them apart. So there are 5 types: G2, F4, E6, E7, and E8, and I use different colors so to make it more easily distinguishable where I am. So the green slides are those of G2 type. There are only 2, one of type 3, one of type 4. And let's not read all of this, but let me just point out some details. So this is also we have in these lists we have given complete lists of maximal totally geodesic submanifolds, also those which are not semisimple, which contain the flat factor from so we have added those found by Berndt and Olmos, but you don't see them here because they are very rare. They only in these spaces there are no such maximal totally geodesic submanifolds. Okay, so then what we see, what are those of maximal dimensions? So here for these spaces here, this 5-dimensional submanifold, this one is obviously the totally geodesic submanifold of biggest dimension. So the one which gives you the index, so the space is 8-dimensional, the dimension of the subspace is 5, so the index is 3 here. So this conjecture of this index conjecture said you always have a reflective submanifold which realizes this index, except for this space. Remember, this is the one, this is the exception among the exception, except for this space. So as we see here, this is not the case for this space. It's the case for every other irreducible space, but not here. So this is the exception among the exception. But in our second theorem, we have said we have this observation about the Duncan index, but still always it is the case, not only for the exceptional ones, that among those of maximal dimension here, there's only 5. There is one with Duncan index, well, 111. If it's not semi-simple here, in this case, this is simple. So the Duncan index is just one number. So we see both of these. And then for the next space, you see here what is the space? There are actually 2 spaces of maximal dimension. One of them is reflective. Yes, that corresponds to this index conjecture. The other one is not, but this conjecture only claims there is one reflective, and there's also one with Dynkin index 1. So let me show you let me go through the next slides it's of course impossible to look through all of these. Oh, well, of course, our paper is on the archive. You can study them in detail if you want. Let me just point out some things here. Oh, for example, here in F4, maybe we look at this. So this space is a rank 1 symmetric space where all of the totally geodesic subspaces have already been classified by Wolf. So this is the Cayley hyperbolic plane, and there are 2 maximal ones. So a real hyperbolic space of dimension 8, and this is a quaternionic hyperbolic space HP2, which appear as both of them maximal dimension. Here, both of them reflective, and both of them of Duncan index 1. So maybe let me just go a bit more quickly through those other spaces. So for E6, we already need 2 slides to list all of them. There are more symmetric spaces, and there are also more submanifolds. Here for the let me go to the next. Yeah, here for the first time you see a flat factor. So those spaces found by Berndt and Olmos, they are much more rare. So they were actually surprised by how many examples we get. We get much more examples. So there's a flat factor here. So we have put it in our lists just to have complete lists. Well, there's the second slide of E6 type. Then we have 2 more slides of E7 type. I don't know what to comment, of course, and we will end with those of E8 type. They are on this slide and on my last slide. Okay, so that's all I wanted to say. I would be happy to answer any questions.
Many thanks, Andreas. Are there any questions or comments? So what would be I mean, this gives the classification in the exceptional cases, but then I guess rank 3 classical are not classified, right?
No, rank 3 is not classified, yeah.
So what would be the smallest dimensional example for which we do not know?
All the totally geodesic. This is I don't know. I need
tricky question. Okay.
This is
never mind. No,
Alberto maybe knows, But we are working on this. Actually, we are working on a classification for rank 3.
Maybe I can say something about.
Yes.
Yeah, go ahead, Alberto. Yes.
Hi. So the thing is here, we are actually, so with our techniques, with our current techniques, we are actually able to classify all those maximal totally geodesic submanifolds in symmetric spaces where the Lie group, where the isometry group of these symmetric spaces has rank less than 8, less or equal than 8. So we can use the same.
Because you use the classification of the graph, right?
Yeah.
Right.
And so for instance, the first case, so we have a problem, for instance, with Graaf-Marranians. If you consider a Graaf-Marranian of 3 planes over R a very big number, then of course we don't know, because as soon as the rank of the isometry group is greater or equal than 8, we cannot use this stuff. So this is what we are trying to do now. We are trying to tackle the rank 3 case. And I also wanted to mention something about your other question regarding isometry. Yeah,
yes.
so as you mentioned, there are 2 kinds of isometry going on here. So either you can consider intrinsic isometries. So this is what we call up to isometric classification. Yes. And you can also consider up to congruence. And I am not really optimistic about getting an up to congruence classification, because there are several technical problems that could arise. So for instance, in the classification by Dynkin, there are already many different conjugacy classes of subalgebras for the same Dynkin index. So this is basically telling you that they could probably arise different congruence classes of totally geodesic submanifolds which are intrinsically isometric. There is also another difficulty, and is that when you go to the real setting, so you have somehow to find not a realification, but you have to find the real analog of your complex embedding, right? So when you do this, you can also create more conjugacy classes. So you can have even more conjugacy classes. And then you have a third problem for me, and it's that the isometry group of this of your ambient space could be disconnected, right? So maybe you are able to say that they are congruent using some isometry of the connected component containing the identity of your isometry group, but there are some other isometries that you cannot really control using linear algebra or at least Lie algebras techniques, right? And so I think the problem will be really difficult, and maybe some approach will be to try to find specific classes of totally geodesic submanifolds where being isometric is equivalent to being congruent. So for instance, reflective submanifolds do satisfy this property. If you have 2 reflective submanifolds which are isometric, then they are congruent. But we don't know about any larger class of totally geodesic submanifolds, of course containing reflective ones, in which this property will also be satisfied. So yeah, I think the problem is really involved, and I don't know that it's even worth it to think about it, because I think it's really difficult.
Yeah. Yeah, I think actually focusing on those isometry classes made this classification possible somehow. I think this was because I mean what Sebastian Klein was always up to congruence, and it's if you look at the papers, it's very complicated. It's very hard. So this is this is actually something that made it possible to classify here.
No, of course, yeah, it makes sense. It's just because we talk about submanifolds, and the naive thing is you say, well, you want to classify up to congruence, right? But then, okay, it's
Yes,
too
yes.
wide, so then it's just it's not going to happen.
Yes, I think in
Yeah, that's a
specific
valid point.
cases, if you were interested in specific cases here in this list, pick one item, you probably can, in many cases, decide if there can be several conjugacy classes by looking at the embedding of the group. This might be possible, I think, but not in general.
But somehow this is also something that so it always happens that this congruence problem makes things really hard. So for instance, in other different contexts, so for instance, the classification of homogeneity one actions, which is also a topic that I have worked in, there is a main difficulty on checking if two given homogeneity one actions are at the end orbit equivalent or not. And to decide this is always a delicate.
Yeah.
So yeah, this congruence problem is always complicated.
Are there any other questions? Emilio has to go. Hi, Emilio. Comments? Well, if not, let's thank Andreas again